Okay, so the last stuff we're going to be going over before the end of the semester is how to name compounds. Two types of compounds, ionic compounds and what are called molecular compounds. Ionic compounds are what we're going to talk about today, and they're what happens when these positive and negative ions come together. Positive ions and negative ions attract to each other, they come together and make compounds. For this semester, for the end of this semester, we're just going to learn about how to name these things. We will eventually start talking about what the electrons are doing that causes the bonds and get into more of the physical details of them. But before we do that, we just want to be able to use the terminology so I don't have to define every word in a sentence as I go forward. Today we're just going to be talking about naming ionic compounds. Let me bring up the PowerPoint here. And naming ionic compounds, if you know how to name the ions, the compounds are literally just putting the ion names together. So it's not going to be that terrible if you know how to do the ions. And yes, you're going to get a worksheet. It's going to be what, Monday for you? I think Tuesday for you guys. Whenever I see you next. Yeah, I guess Monday. I think I see you guys Monday. But the worksheet will be due next week, whenever I see you the first time next week. And it's a lot of practice because this is one of those things where it's really important that you know how to do it. It's not that hard to do, but I really want to kind of burn into your brain because as we go forward, we start talking about chemical reactions and stuff. If I say, you know, this thing has calcium chloride and you don't know what that means, you may as well just give up all the points on that question because you don't even know what the starting material is. So it's a simple thing. These are, you know, relatively easy points as long as you learn the couple rules. So it would be to your benefit to do that because this is going to keep coming back. A lot of the stuff we're learning now in chemistry is it's not like next unit it's going to go away. We're going to keep having to know chemical names. So a little bit on the history. There is a system, a logical system for chemical names and formulas. That didn't always used to be the case. There was a time when chemicals just had common names and those names had nothing to do with their formulas. And we still do that. We still have chemicals that have common names. Water. The word water has nothing to do with what is in water. It doesn't tell you that there's hydrogen and oxygen in water at all. Now, most people do know that water is H2O. But if you had to do that with every chemical, memorize a name and then memorize an entirely unrelated chemical formula, and remember that those two things are connected, that'd be a pain in the butt. So early on, when chemistry became modernized around the 1790s or so, we started coming up with a system to relate the names to the formulas and the formulas to the names. So that if you knew the formula, you could figure out the name and vice versa. So we just said the name of something, you know what's in it. A couple other examples of like chemicals that used to have names that have nothing to do with the formula, like potassium carbonate, K2CO3, used to be called potash. It was called potash because you got it by boiling ashes, literally charred wood in a pot, and that would give you some potassium carbonate. Not very pure, but it was the best they could do at the time. NaHCO3, so sodium bicarbonate, still called baking soda. Baking soda is a chemical. It's used in baking to make baked goods rise, which is why it's called baking soda. But that tells us nothing about what's in it. So it is much easier to say the words potassium carbonate, know that this thing is made out of potassium and carbonate, or sodium bicarbonate, know it's made out of sodium and bicarbonate. These names, the modern names, reflect the formulas and vice versa. And just so you know, there are, and we're not going to learn what cinnabar is, it's a more complex ionic compound, but the ionic compounds we're talking about, they make up like most of the Earth, most of the mass of the Earth is actually ionic compounds. It's crystals. Minerals and rocks are mostly ionic compounds. Now, not simple binary ones like we're going to learn. Well, they're all simple binary ones. They're more complex. But this red substance, which is a mineral called cinnabar, is a complex ionic compound. But cinnabar, that doesn't tell you what's actually in this. I believe this is lead, oxygen with a little bit of tungsten. It's got a complex combination of ions and anions and cations, but it doesn't help us to know, just the name doesn't help us know what's in there. And if you think of like gemstone names, gemstones are for the most part, with carbon aside, are for the most part ionic compounds. The names don't tell you what's in them. We know what's in them mostly now, but the names don't help with that. So when working with chemicals in the field of chemistry, we use a proper system of names. And yes, this is a Lavoisier thing. He did this primarily. He did a lot of the stuff that made chemistry into a modern science. He and a Swedish guy, John Berzelius, came up with a system to properly name and write the formulas for chemicals so that the names and the formulas go together. And most of that is still what we use today. It's been expanded upon because we have more complex chemicals, and different branches of chemistry have slightly different naming systems. So like organic chemistry, if any of you are going to be pre-med, you have to take organic chemistry. They have their own naming system for different long chains of carbon, because organic chemistry is all about long chains of carbon. But for our purposes, we're going to start with the very simplest stuff, which is binary compounds. Binary compounds are, by definition, the simplest compounds. Compounds have to have more than one element, and binary compounds have two, which is the least you can have that is more than one. So we're going to learn how to name binary ionic compounds today, and then next week, binary molecular compounds. So we're doing basically just two parts. And for ionic compounds, you literally just put the names of the two parts together, and that's the compound name, as you will see. So the big thing here, though, is if you know the name, you can write the formula. If you know the formula, you can write the name. Like with a couple rules, given one of those pieces of information, you can figure out the other one. And that is quite helpful. So here is a picture of them smelting iron ore to make steel. Steel's like 80% iron. They used to do that here, but you know, industry went away. So we're Rust Belt City now. But yeah, this is how they make steel. And one of the most common iron ores, hematite, primarily contains iron in this compound. So you don't just dig up hunks of iron out of the ground. It's in a compound and you have to separate it chemically. Smelting iron ore is actually a chemical process separating the iron from, in this case, oxygen. So iron 3 oxide. That name tells us what's in it. It tells us that it's made of iron 3 and oxide. So iron and oxygen in ionic forms. So I'm going to go to the whiteboard to do this. Just bring up the thing. Sorry, I'm take a couple extra clicks because I'm recording this for, I'm not going to be here tomorrow for the G period. So I want to make sure they have the same experience you do. There we go. Or do it. There we go. Okay. Hopefully that's correct. Okay, hopefully they're seeing the right screen there. So, iron 3 oxide. Well, that's two ion names, right? Iron 3 ion, oxide ion. We should be vaguely familiar with naming those things. And all that means it's made of those two ions. Oxide is oxygen. Oxygen. Third last column on the periodic table, just 2 away from being a noble gas. What charge does oxygen take when it becomes an ion? What is an oxide ion? What charge does it have? Yeah. Negative what? How many electrons does it want to gain?
2.
2. Yeah, it's 2 away from being a noble gas. It has 8 electrons. It wants to have 10. So oxygen and that whole column wants to become -2 ion. It does. So oxide is -2. Iron 3, well, iron's one of the ones that gets a Roman numeral, clearly. The reason it gets a Roman numeral is because it can have more than one charge state. It can be iron 2 or iron 3. So we know which one it is. It's iron 3. And whenever you see a Roman numeral, that is the positive charge. So Fe+3. So that is what iron 3 oxide is made of. It's made of this thing and this thing. Now we have to figure out how they go together. And the key with ionic compounds is that the charges have to all cancel out. Ionic compounds combine in such a way that the net charge, the overall charge, is 0. So we've got something that's +3 and something that's -2, which seems like it's going to be a pain to do that with it. And this is actually about as hard as it gets. But if we want to combine them, well, we need to find the least common multiple of 3 and 2. That's the only way you're going to get them to cancel out. What's the least common multiple of 3 and 2? 6, right? Yeah. So how many irons would you need to get to +6? How many irons would get you to +6? 2. And how many oxygens would get you to -6? Yep. 3. So yeah, we have 2 of these and 3 of these. They actually end up balancing out. And one way to check that, that I like to do at least when I'm starting this is I just write all the charges. I got 2 + 3, +3, +3, -2, -2, -2. And that all equals 0. And it should. Ionic compounds always end up equaling 0. So you can always figure out how many of each thing you have because they have to equal to 0. So that is the very basics of how that works. And again, all it is, it's the name of the cation, the positive thing, followed by the name of the negative thing. By the way, the positive one's always going to come first. The negative one's always going to go second. That's true in both the name and the formula. They're always going to be in the same order. So I'm going to do some examples. And I'm going to briefly, I want to talk about, this is another way, and this is up online. This is another way to figure out the least common multiple, or at least to cancel out the charges. It's called the Crisscross Method. If you write the ions out, their charges should be superscripted because that's how you write ions, if their charge is above. You can just take the charge and bring it down to the opposite one. And it works. And it seems like it's easier, but in the end, it actually ends up being more work usually. So you can do it. It's fun. There's nothing wrong with doing it this way. But I'm going to show you where you kind of might get in a little trouble if you do it. So with iron oxide, iron 3 oxide, it works perfectly. The 2 comes down, goes to the iron, the 3 goes over there with the oxygen. Works out fine. The one problem you end up with is when you have something like this. So let's say we have a calcium and a sulfide. Calcium sulfide, calcium's in the +2 column. There's 2 more than the nearest noble gas, which is argon. Wants to lose 2 electrons, it becomes +2. Sulfur, also 2 away from argon, but negative, 2 less than argon, so it wants to gain 2 electrons. So we got a +2 and a -2. And most of you at this point would just go, okay, they balance out. We need 1 of each. And you'd be 100% right. That's what you need, 1 of each. +2 and -2 just balance. But if you're just kind of in the habit of doing the crisscross method, you might end up bringing the 2's down, get Ca2S2. Well, ionic compounds always have to be written in lowest whole number form. So, screen here. So if you did this, again, with like Ca+2, S-2, you just brought that down to there, that down to there, and got Ca2S2. This is not a lowest whole number ratio, right? You have to then reduce to lowest whole number ratio, which in this case would be 1 to 1. And we don't write the 1s in as subscripts. We just assume them. So it would just be that. As long as you remember to reduce, the crisscross method will always work. It's just kind of unnecessary. Like it's a +2 and a -2. Just go with it. The hardest you're going to get is basically 2 and 3. Remember, we don't get much bigger than 4. It's +4 and -4, pretty much the biggest you're going to see. So usually you can just do it in your head and kind of live with it. That is just my suggestion. I don't mind the crisscross method. I just notice people often forget to reduce to the lowest whole number terms, and they lose points they wouldn't otherwise lose. So any question? Yeah.
So with the crisscross method, every time you do that, you have to reduce?
Well, if it can reduce. Like 2 and 3, that's already the lowest whole number ratio, right? So if you did it with iron 3 oxide, you know, the 2 and 3, you're all set. But yeah, if you get like 1 and 1, or sorry, 2 and 2 or 2 and 4 or something, yeah, you would reduce it to the lowest whole number ratio. So yeah, you have to check, and then you just can reduce it after that. But with a lot of these, again, you can do these all pretty much in your head. There's not like, you don't have to do the crisscross method because none of these numbers are going to be bigger than 4 for the most part. And I trust that all of you can deal with that, no problem. Before we do anything else, if you have your polyatomic ions, just get them out because I'm going to talk about polyatomic ions. And it's just, I want you to be in the habit of kind of looking at polyatomic ions and seeing what I'm talking about instead of just kind of vaguely staring off into space as I talk about them. I had mentioned the polyatomic ions, they act just like regular ions. They're just made of more stuff. And the way you know when given a name that you have a polyatomic ion, or the big clue, is the ending of the second part, the anion. Polyatomic ions are for the most part anions. There's only one positive one. And if the anion ends in ATE or ITE, it's on the sheet. All the anions, all the negative charge things from the periodic table end in that IDE ending. So fluoride or chloride, or if this was nitride, that would just be from the periodic table. But this is barium nitrate, ATE. So you look it up. And that's really all you have to remember, because on the periodic or on the polyatomic ion sheet, excuse me, it gives you the formula and gives you the charge, which is what you need. So first, let's look at barium. Barium is on the alkali earth metal second column on the periodic table, and that whole column becomes +2. They want to lose 2 electrons to be like the nearest noble gas. So barium is +2, and nitrate, ATE, is NO3 with a negative charge. And I'm going to show all these examples of the crisscross method, because back when I made animations, I actually did that. But if we have a +2 barium and a -1 nitrate, how many nitrates do we need to balance it out? How many -1s balance out a +2? Yeah. Yeah, 2 of these balance out one of those. This one's twice as much. 2 of those balance out one of those. And that's really all it is. So you can, and absolutely, if you want to, you can do the crisscross method. There's nothing wrong with it, and it will get you the same results, but you just probably don't need to. So charges don't balance. You can do the crisscross method, and you bring the 2 down here. Now, this is an important thing. The blue background. This projector used to be more bright, I swear. So one thing about polyatomic ions, when you need more than one of them, you have to put them in parentheses, because if I were to just write like barium nitrate like this, just put the 2 there, that just means I have 32 oxygen. That's not what we want. So we just put this in parentheses and say we have 2 of all that thing. So if you have a polyatomic ion, you need more than one of it, you just put it in parentheses. If there's only one of them, you don't need to put it in parentheses because you're not multiplying it by anything. But if you have more than one, you put it in parentheses just to show that all of this thing, you need 2 of. So I'll go through a couple more examples, and then I'm going to talk about going the other way, given the formula writing the name. Then, it'll be time for you to work on practice stuff. So ammonium sulfate. This is the most complex you're ever going to see pretty much. This is 2 polyatomic ions. Ammonium. I would strongly urge you to take a note that ammonium is on the polyatomic ion sheet. It's the only positive thing on the polyatomic ion sheet. So people tend to forget about it because like every other positive thing is just from the periodic table. And I will get people intently staring at the periodic table on testing quizzes. And eventually, like after 5 minutes, they'll raise their hand and go, "Where's ammonium?" And then I'll point out their polyatomic ion sheet. And that's just a waste of 5 minutes. So it's not a big deal, but it will save you some time and frustration probably. Ammonium is the very last one listed on the polyatomic ion sheet I gave you. It's NH4 with a +1 charge. Sulfate, also on the polyatomic ion sheet, is SO4 with a -2 charge. And anyone who can count knows, you would need 2 +1s to balance out a -2. You're going to need 2 of these guys. 2 of these guys, 1 of these guys, that will balance. The crisscross method will absolutely get you there as well, as you can see. And because we need 2 ammoniums, 2 of this whole thing, we do put it in parentheses because we don't want 42 hydrogens, we want 2 ammoniums. So we bring the 2 down, and that's it. You don't need to put sulfate in parentheses because there's only one of them, so it's unnecessary to put it in parentheses. No, I didn't want to do that. Sorry. So, kind of makes sense. Think we're doing okay on this? Okay, I'll do one more example, then we'll switch to go in the other direction. So, iron 3 chloride. When you're given a name, the Roman numerals actually help you out. Going the other way, they can be a pain in the butt. You have to remember when to use them and when not to. But if you're given the name, iron 3 chloride, that 3 tells you the charge. You don't have to look up. You don't have to look up iron and figure out where it is in the periodic table. No, it's +3. It's iron 3. It's +3. So you got iron 3, which is 3+, because again, the Roman numeral tells you the positive charge, and you've got chloride to halogen right next to noble gases. So they want to gain 1 electron and become a -1 ion, and they do. And since you've got a +3 and a -1, well, you're going to need 3 of these guys. You need 3 chlorides to balance out the iron 3. And that's what ends up happening. You end up with 3 chlorides. And there you go. So that's iron 3 chloride. And that's really all there is to this. It's not, I'm not going to say it's the easiest thing in the world, but certainly the math here is not as complex as some other math we do. There's no scientific notation. It's 1 through 4, which are all numbers you know. So I'm going to skip. There are some more examples up here if you want to look at them, but I don't think I need to go through every example. So what I want to talk about now briefly is going the other way. Given the formula, what is the name? So we talked about going from name to formula. Now we're pretty much just reversing the rules and going the other way. So CS2O. CS is cesium, which is an alkali metal. So this is going to be made of a metal and a non-metal. It's going to be cesium and then oxide. And that's all we're going to call it, cesium oxide. We don't have to do anything special about it. Anytime you have a metal combined with a non-metal, that's an ionic compound. So cesium is a metal, not like a commonly used metal, but yeah, it's a very, very reactive metal. So not incredibly commonly used, but it is a metal, and oxygen is definitely not a metal. So it's an ionic compound. So you just name the cation, cesium, name the anion, oxide, and shove those 2 things together. Cesium oxide. NABR. NABR is made out of a sodium ion. That's the positive part. And a bromide ion, which is the negative part. So we just call it sodium bromide. We literally just put the 2 names of the ions together and call it a day. SRF2 is made out of strontium, a strontium ion, and a fluoride ion, and we just call it strontium fluoride. So when naming it, you literally just give the name of the cation and give the name of the anion. Positive thing first, negative thing second. Most of the time, it's really simple, but the Roman numerals are going to make this a pain in the ass a little bit because that's how it goes. So let's look at copper for an example, or copper with oxygen. So let me go back to sharing the screen here. There's like a 90% chance this recording just straight up doesn't work, just because I'm that lucky. There we go. So let's say we have copper combining with oxygen in the formula CuO, a 1-to-1 ratio. Now, this is a thing that exists. It's a real thing. The problem is, this is also a real thing. So we cannot just call both of these things copper oxide, right? They're clearly different things, and we have to name them differently. And we're going to do that with Roman numerals. Copper is one of the elements that gets Roman numerals. The elements that get Roman numerals, when they become ions, this PDF is up on module 7. But if you remember, it's the D block, but not zinc, cadmium, and silver. And then tin and lead in addition to those. Those are the ones that get Roman numerals. Kind of just have to know when to use Roman numerals. They get Roman numerals because they can be more than one thing. In fact, like copper's the example I put on here, copper can be +1 or +2. And so we have to specify. Almost all of them can be +2. Some of them can be +2 and +3, +1 and +2, +2 and +4. It's just sort of, it has to do with very complex exceptions to the Aufbau rule and flipping between s and d orbitals and stuff. So we're not going to get into the specifics of that, but they can have more than one charge, so we have to specify. So to figure out what's what, first of all, I like to just go like this. When I'm naming it, it's going to be copper, and then I put the parentheses for the Roman numeral, and then oxide. So before I even figure out what the Roman numeral is, I just get the whole rest of the stuff, because the Roman numeral is going to be the hard part. And I'm going to do the same thing for this one. Just copper, parentheses, oxide. Because we know the negative part's oxide. There's no question about that. Now, oxygen, as we talked about, always takes a -2 charge. To figure out what the Roman numeral is, we have to figure out what the charge on copper is, what the positive charge here is. And we know two things. We know oxygen's always -2, and you also should know, going forward, that these two things have to balance out. If you're given a formula like CuO or Cu2O, it's balanced. The positives do balance the negatives. I'm not going to give you a formula that's not balanced unless I make a mistake, which does happen, but that's on me and not you. So if we know this side is -2, and I know on this side I have just one copper, what must that copper be to balance it out? Yeah.
Copper 2.
Yeah, copper 2. It has to be +2. +2 balances out -2. So we get copper 2 oxide over here. Now on this one, and this is where it can get a little bit more difficult because you just have to remember you have two coppers. And the coppers are going to be the same thing. You can't have like one copper 2 and like half copper 2 and half copper 3. They're all the same thing. So if you got two coppers, what would each of them equal to balance out -2? Yeah. Copper 1, sure. If we do +1, +1, -2, that balances out, right? So this one is copper 1. Be very careful here because the Roman numeral is the charge on the copper. It isn't the number of coppers in the equation. It's the charge on the ion. That is a common mistake, and it's an understandable mistake, but it is still a mistake and still wrong. So because this has a charge of 2, you only need one of them to balance out the oxygen. Because this has a charge of 1, you need 2 of them to balance out the oxygen. And that is, I mean, about as difficult as this gets. Remember to use Roman numerals when you need to use Roman numerals. So what I'm going to do now is pass out the worksheets. You'll have the rest of today to do the worksheet. And I will probably give you sometime in class on Monday, I believe, to ask questions, go over some answers. I'm going to go over how the worksheet is to be completed, just because it's not necessarily super straightforward. So the first page is just review for ions. These are all just ions. The bottom part is polyatomic ions. You literally just have to look those up and put the names up. But it's just like the worksheet you just turned in. So ions. The second page and third page have these charts. That look kind of like this. And what you're going to do is on the charts, on the side, there's positive cations, and on the top, there's negative anions. And in each cell, you just combine that particular cation and that anion. Remember, the charges have to balance out. So in the top corner, Na plus and Cl minus, they become NaCl because +1 and -1 already balance out. Always write the positive thing first and the negative thing second. So the positive thing always goes first, the negative thing always goes second. For the second part of that, it's the exact same thing, except I gave the names. I want you to write the formulas right under the names and then do the same thing. The third page gives you enough information in each column to fill out the rest of the information in the column. Each column is slightly different. So you have the name of the cation, name of the anion, formula of cation, formula of anion, formula of the compound, and the name of the compound. And you have enough information in each column to fill out everything else. So, do that. Last page, this one's simple again. If you're given the name, write the formula. If you're given the formula, write the name. Again, remember when to use Roman numerals. That tends to be the biggest hiccup. Is the Roman numerals. when to use them, and also that the Roman numerals stand for the charge and not the number of atoms. So the Roman numerals stand for the charge, and also know when to use them. So you guys can work by yourselves, you can work in groups, but you have the rest of this class to work on that. And again, you'll have some time on Monday as well. Get it as much finished as you can, I would suggest. But I will take some time and take questions and stuff. I don't think I'm going to put a key up for this, but for any names or formulas, you can literally just type it into Google and it will give you the name of the formula. It's pretty easy. And you don't have to type in proper here, like subscript. So if we had we did iron 3 chloride, Fe, Cl, I'll just put the 3 here. And look, there it is, iron 3 chloride. So you can check very quickly this way. So I probably won't make a key because it's very easy to check these things. So just so you know. Okay, go ahead and work. If you have questions, ask. That's kind of it for today.